Welcome to this explainer. Today, we're going to unravel one of the absolute greatest scientific mysteries in history, the true nature of light.
Let's kick things off by diving into a historical detective story, asking the fundamental question that literally divided the greatest scientific minds for centuries. Is light made of tiny, incredibly fast-moving particles, or is it a continuous wave just rippling through space?
So, here is our agenda for today. 1. The nature of light. 2. Understanding wavefronts. 3. Huygens principle. 4. Interference and superposition. And 5. Diffraction and polarization. We're going to trace this entire academic journey step by step.
Starting right off with Section 1, the nature of light, the great scientific debate.
To really understand this debate, we have to jump back to the 1600s. Scientists were desperately trying to figure out what was actually traveling from a candle flame to their eyes. You had Sir Isaac Newton on one side with his corpuscular theory. He visualized light as these tiny, perfectly elastic balls. He called them corpuscles, just shooting out at crazy high speeds. On the flip side, you had Christian Huygens with his wave theory, suggesting light was a wave traveling through this invisible, universal medium called the ether.
Now, Newton's theory made a ton of sense if you think about a thrown ball bouncing off a solid wall, right? It successfully explained basic reflection and refraction. But it completely fell apart when it came to other behaviors. His corpuscular model couldn't explain interference, diffraction, or polarization. It simply couldn't explain why light sometimes bends into shadows or, paradoxically, creates dark bands when it overlaps. Think about it. If light were just physical balls, adding more balls together should always make things brighter, never darker.
Which brings us to Section 2, Understanding Wavefronts, Visualizing the Invisible.
Since the particle theory hit a wall, we turn to Huygens' wave theory. But to truly grasp it, we have to visualize how a wave actually moves through space. At its core, a wavefront is simply the locus of all particles in a medium vibrating in the exact same phase. Picture dropping a stone into a totally still pond. That continuous, expanding circular ripple where all the water peaks at the exact same time, that is exactly what we mean by a wavefront. It's a perfectly synchronized boundary of disturbance.
And depending on the shape and distance of your light source, these wavefronts take on three distinct geometric shapes. First, you have a spherical wavefront, which emanates from a single point source, expanding outward in all directions, kind of like a balloon. Then, you have a plane wavefront. This one arrives in completely parallel lines, which happens when the light source is practically at infinity, like sunlight reaching Earth. Finally, there's the cylindrical wavefront, which radiates outward from a linear source, kind of like a really long glowing tube light.
So, what happens when one of these waves hits something? Let's take a plane wavefront hitting a convex lens. Because light travels slower in denser mediums like glass, the center of the wave hits the thickest part and gets slowed down the most. Meanwhile, the outer edges pass through the thinner glass and actually move ahead faster. This causes the flat wavefront to literally change shape, emerging beautifully curved and converging into a spherical shape.
Moving on to Section 3, Huygens' principle explained, the geometry of light propagation.
Now that we know what wavefronts look like, let's look at the math behind how they move forward. Huygens introduced this brilliant concept called secondary wavelets. He proposed that every single microscopic point on a primary wavefront acts as a fresh, independent source of new disturbance. So a wavefront isn't just one solid, rigid wall moving through space. Actually, it's more like a collection of countless tiny new waves continuously being generated all at once.
So how do we find the overall wave a split second later? Well, the new position of the wavefront is simply the forward envelope or tangential surface of all those secondary wavelets combined. Basically, if you wrap a smooth surface tightly around the very front edges of all those tiny expanding ripples, boom, you get the actual new position of the overarching wavefront.
And here is an absolutely crucial geometric rule to always remember. A perpendicular drawn to the surface of a wavefront at any point in the direction of propagation gives the ray of light. Meaning, the actual ray of light you see is always shooting out perfectly 90 degrees away from the wavefront itself. If your wavefront is a flat wall, your rays are straight arrows pointing directly away from it.
Using this exact step-by-step geometric construction, Huygens was able to flawlessly prove the law of reflection, where the angle of incidence equals the angle of reflection. Imagine an angled plane wavefront striking a mirror. The bottom edge hits first, instantly generating secondary wavelets that bounce back. Meanwhile, the top edge is still traveling forward in the air until it too hits the mirror. By tracing the forward envelope of all those differently timed bounced wavelets, you perfectly derive the exact geometry of the new reflected wave.
It is so elegant.
Let's look at Section 4, Interference and Superposition when waves collide.
We're going to explore what happens when two separate light waves literally crash into each other using the principle of superposition. When constructive interference happens, crests line up perfectly with crests. Their displacements add together, resulting in a higher combined amplitude and a really bright fringe of light. But when the crest of one wave perfectly meets the trough of another, we get destructive interference. They completely cancel each other out, creating a dark fringe. This phenomenon, where light added to light actually creates absolute darkness, is the ultimate proof that light behaves as a wave. Newton's bouncy ball theory had absolutely zero explanation for this.
Now, instead of getting totally bogged down in all the mathematical derivations right now, just think of these essential formulas as your tools of the trade. You have the basic interference formula, delta x equals n lambda, to calculate the path difference for bright fringes. You've got Young's double-slit equation to find the precise physical position of those fringes on a screen. There's the Rayleigh criterion for measuring the resolution of optical instruments and Brewster's law for calculating polarizing angles. These are your cheat codes for predicting exactly how wave optics behave mathematically.
And finally, Section 5, Diffraction and Polarization, Bending and Filtering Light.
Let's examine two more spectacular phenomena that definitively confirm the wave nature of light. First up is diffraction. This is the bending of waves around the corners of an obstacle or through an aperture, bleeding right into the geometrical shadow region. If you've ever noticed how light softly bleeds around the edges of a slightly opened bedroom door in a dark hallway, you are witnessing diffraction in action. A strict particle beam would cast an incredibly sharp shadow, but waves naturally bend around boundaries.
When light is forced through a very narrow single slit, this bending creates a highly specific diffraction pattern. The light intensity actually drops to exactly 0 at angles where n times lambda equals a times sine theta. Because the different parts of the single wavefront passing through that tiny slit actually interact with each other, we don't just get a single line of light. We get a massive, bright central maximum flanked by slowly fading dark and bright bands.
Next is polarization, which proves light is a transverse wave by restricting its vibrations to a single plane, successfully filtering out other directions. See, while Huygens correctly guessed light was a wave, he wrongly thought it was a longitudinal wave, pulsing back and forth like sound waves. Polarization proved the vibrations actually happen perpendicularly to the direction of travel. Think of it like wiggling a jump rope up and down rather than pushing it forward.
Decades later, James Clerk Maxwell's brilliant electromagnetic theory stepped in to perfect Huygens' initial idea. Maxwell proved that light is an electromagnetic wave, it's transverse in nature, and it travels at a staggering finite speed of 3 × 10⁸ meters per second in a vacuum. Most importantly, he proved it does not require a mechanical medium like that imaginary ether to travel through. It just propagates through oscillating electric and magnetic fields.
And that realization brings us to a mind-bending final question that really sets the stage for modern physics. If light is an electromagnetic wave traveling through a complete vacuum, if it has absolutely no mass, and it doesn't need an ether, how can something travel as a wave through completely empty space? What exactly is doing the waving? Well, I'm going to let you chew on that one. Thanks for joining me on this deep dive into the fascinating world of wave optics.